Assalamualaikum and a very good day to you all. In today's video, we are going to talk about fragile fat bearings from the Shigley Mechanical Engineering Design book. Okay, so let's begin. So fragile fat bearings, the load carrying capacity of self-contained natural circulating general bearings is quite restricted. The factor limiting better performance is the heat dissipation capacity of the bearing, meaning that in order to bearing to become properly perform, the heat dissipation must be a better one. If the heat is contained in that bearing, it will be problematic because the heat cannot flow and the heat temperature will rise and everything, and then become wear and tear, and the lubricant become the viscosity of the lubricant will also become so fluidic, and then uh, it defeats the purpose of viscosity. So this subtopic we're going to discuss about fragile fat bearings. Okay, so how to overcome this problem and everything. The first thought of a way to increase heat dissipation is to cool the sum with external fluid such as water. Meaning that when the bearing is hot, you pour water to it, uh, and uh, it will dissipate the heat. Okay, the high temperature problem is in the film where the heat is generated but cooling is not possible in the film until later. Okay, so because the film is located inside, it's not the outside of the bearing. Okay, you can see the diagram, the picture that I taken from Google. I taken this picture from Google. You can see this picture. The journal itself is located inside. Okay, if you pour water, if you pour water, the water will go only outside. It doesn't go into inside. So this is the amount of problem. Okay, this does not protect against exceeding amount of allowable temperature of the lubricant. A second alternative is to reduce the temperature rise in film by dramatically increasing the rate of lubricant flow. Yes, if you put more lubricant, uh, then okay, the lubricant itself is reducing the temperature rise. A water cooled sum may be still be in the picture. To increase lubricant flow, external pump must be used with lubricant supplied at pressure of 10,000 pounds per square inch. Because lubricant is applied to the bearing under pressure, this bearing is called pressure fed bearings. This because you supply lubricant all the time. Okay, this is what they call pressure fed bearings. Okay, if you can remember this picture, the hydrodynamic theory, or the theory uh, of general bearing and everything, most of them is based on this diagram. Okay, based on this diagram and theory, you can Google it. Okay, forcing greater flow through bearing. To force a greater flow through bearing and thus obtain an increased cooling effect, a common practice is to use a circumferential groove at the center of the bearing, uh, which an oil supply hole located opposite of the load bearing zone, just as bearing in figure 1227. Okay, next slide. The effect of groove is to create a two-hub bearing, each having a smaller diameter L/D ratio than original. The groove divides the pressure dissipating curve into two lobes and reduce the minimum film thickness, but it has wide accepted among lubricant engineers because such bearing uh, carry more load without overheating. Okay, so better because in the end the purpose is for bearing to carry more load. When carry more load, is subject to overheating. But if you put the groove larger, uh, the overheating problem will become solved. Okay. Solution for airflow. To set up a method of solution for airflow, we shall assume a groove sample enough that the pressure drop in groove itself is small. Initially, we will neglect eccentricity and then apply a correction factor for this condition. Okay. Uh, the oil flow is then is the amount of flow of the two half of bearing in direction of concentrating shaft. If you neglect the rotation of the shaft, The flow of lubricant is caused by supply pressure, PS, shown in figure 1228. Okay. If you have the textbook with you, you can open figure 28. Okay. Laminar flow is assumed where the pressure varying linearly from PS at x equal to 0 and P equal to 0 at x equals to L. What does it mean by this statement? Okay, pressure vary linearly from x equal to 0. Okay, you can imagine this in x-axis, okay, x-axis, y-axis, and this is the length. The x-axis meaning that the beginning of the flow, okay, meaning that the pressure is 0, no pressure yet, and x equal to L. This is the L. If this is the length of the journal, you see, if this is the length of the journal, is x equal to 0, x become to L. Okay, so x equal to P s at beginning, and x equal to 0 is at 0 at L location. Okay, consider the static equilibrium of thickness dx, the height to y, and unit depth. Okay, so this is the equilibrium equation. Note particularly that origin of reference have been chosen at the midpoint of clearance space, and symmetry about the x-axis implied with the shear stress T being equal on the top and bottom surface. The equilibrium equation in the x direction is this. This is the equilibrium direction. If you can see the picture, you can see where is the location of x, y, and shear axis. Okay, expanding and considering the term, you get shear equals to y dp over dx. Okay, the pressure over length, and the y is this axis, x is this axis, pressure distribution. Okay, this is the shear stress. There is a video concerning about the flow. Then the video states that the particle of the flow uh, have shear stress. Okay, like this. There is one video. Okay. When the flow like this, okay, this both up and down region has shear stress. Both have shear stress. Okay, like this. There is a one video. Can record. Imagine you take one particle, one element of a particle. Imagine one element of particle. The flow moving like here, and this is the pressure coming at the front, and this is the shear stress up and down of the particle. Okay, eliminating shear stress from the equation B and C give du. U is the velocity of the lubricant. Remember, in doing this subject, there is capital U and small u. Okay, there is a capital U and also small u. This small u is the lubricant flow in the lubricant. Okay, u is the flow of the something uh, on the lubricant. Imagine, like you can imagine a ship flowing, a ship moving on the water. Okay, the ship moving at certain velocity is capital U. Okay, the water moving inside the water is the small u. This is the u. You can relate this analogy with uh, you can relate this analogy with the general bearing. Okay, and then treating dp per body as constant and integrating the with respect to y give u equal to this equation. Okay, and as boundaries where y equal to plus minus c over 2, meaning the clearance, okay, velocity is u is 0, using one of these condition. Okay, give 0 equal to this equation, and you get c1. Where is y equals velocity u is 0? Where is this location? Okay, okay, where is this location? You can imagine this boundary. This is a journal. Okay, this is a journal bearing, and then this is the y-axis, okay, and x-axis is the length of the, okay, is the length. This is the x-axis and y-axis, okay, here. And then there is a clearance here, clearance. You learned about clearance in the previous video, okay. And this is the y plus minus 2, okay, here, okay. And at some point velocity is 0, meaning that the lubricant cannot flow somehow. In a condition, one condition is so small that lubricant cannot flow, okay. This is y equal to 0, okay. So then you can get the constant ce1, and then u equals to this equation, and then assuming pressure varies linearly from p to 0, x equal to 0 to L respectively, s equal to 0 to L, okay. And pressure can be written as P equals to Py minus Ps over L, and the pressure gradient is given by P dP per dx, so Ps over L. Then you can substitute this equation to become U equal to this equation, okay. Ps 8 UL C power 2 minus 4 Y power 2, okay. So from figure 1229 show a graph of this relation fit into the clearance space C, so that you can see how the viscosity, how the velocity of the lubricant varies from general surface to the vary surface. The distribution is parabolic as shown with maximum velocity occurring at the center where y equals to 0, okay. So magnitude is from equation 1231, u max equal to ps uh, c power 2 over 8 UL. Okay. To consider eccentric as shown in figure 1230, the film thickness is H equal to C minus eccentric. Okay. What is eccentric? Just want to remind you, when you put the journal, of course, the journal, because of the weight of journal, the center location from 00 location is not going to be perfect. This is concentric. This is called concentric. This is, let's say this is the bushing. This is the my marker pen is like a journal bearing. When you put inside here, okay, it cannot be at the center 00 position for both. It will go down, okay, because of gravity. Okay, it go down, and then this is called the, because the center location is not 00 location. Okay, so it become concentric. Okay, it become eccentric. Okay, so if when you put eccentric in the equation, you get this equation, equation u a v a u average, this equation, okay. uh, so this is the pressure distribution of lubricant velocity. Of course, you can see here, you can see here u maximum. If you can recall from the first video on hydrodynamic theory, the video states for Buckham Tower, talking about how that he get this theory on pressure lubricant. This is the theory, okay. You can see, if you drill a hole, let me recall back the first video on hydrodynamic theory from Buckham Tower. You drill a hole here, you put anything to cover the hole, corkscrew or screw or anything, that screw will fly away because the pressure distribution is so high, okay. It is at this location, you can see it high. If you see it from this location, if you see from this location, you, it will just go up like this, okay. It will just go up like this from xy, from x, this view, okay. If you see from this view, it will just, the pressure distribution is like this. If you see from this view, this pressure location is like this, okay. You can refer back to the video on Buckham Tower. And okay, side flow for energy position is dqs ds. Okay, for dA is elemental area and substitute from J to H, figure 1230 give this equation. What is a side flow? Okay, of course, for any general bearing, the length, the left and right, there will be an ending for it. Okay, this is called the side flow. Uh, okay, this side flow. Okay, this equation for the side flow. Integrating around the bearing give a total of this. The range become like this, and analyzing for formula of pressure fat bearings, the bearing length should be taken as L prime as defined in equation 1228. The characteristic pressure in each of the two bearing that constitute the pressure bearing is assembly is given by this equation. Okay, P equals to over W over 4RL. W is the weight, the load, which meaning that the weight of the journal itself. Okay, and for RL, R is the radius of the journal, radius of this, L is the length of this. Okay, this is figure 1230. You can see the location of concentric and everything. Okay, this is, you can remember there is a one equation involving concentric. In order to get the equation, it consider first no concentric happen, but in reality there is concentricity. Okay, there is eccentricity here. Eccentricity meaning that the location for 0 0 is not the same. Okay, the charts for flow variable and flow ratio in figure 12 9 19 and 1220 do not apply to pressure bearing. Okay, also the maximum film pressure given by figure 1231 must be increased with oil supply pressure, PS. PS stand for supply pressure. Okay, to obtain total film pressure, since the oil flow has been increased by force speed. Okay, if we give a temperature rise that is too high because side flow carries away all the heat generated. The plumbing in the pressure bearing is depicted schematically in figure 1231. The oil leave the sum as internally maintained temperature, TS. Okay, TS is the temperature of the supply. Okay, the temperature of the supply. Okay, S for supply. Okay, PS oil supply pressure, TS temperature for the supply. Okay, and this is volumetric flow rate for supply. S is for supply. The heat gain of fluid passing through bearing is the heat gain. This is the equation for heat gain. At steady state, the rate of the which does frictional work is given by this. Okay, this is H is for heat. Okay, so 2 pi W N C over J F R over C. Okay, and then this is the pressure fat central location on full annular growth journal bearing with external coil lubricant sum. This is the picture. If you don't understand this picture, you just Google pressure fat bearing. There is some picture diagram, 3D diagram of it. You can imagine, you can relate this picture with that picture from Google image. Okay, equating the heat gain from frictional work and solving this temperature variation give this equation. Substituting the side flow equation give this equation. Sommerfeld number, yes, the Sommerfeld number, you must remember the equation for Sommerfeld number. I want to emphasize that you must be correct. If you done wrongly calculate, everything will wrong. Okay, the whole question will be wrong. If the question is 20 marks, all 20 marks you will get wrong. Okay, Sommerfeld number is important for you to know, for you to memorize. Okay, solving for equation, Sommerfeld expression, substitute the expression J equals to 9336 BTU. Okay, you can get this, and then you get uh, the radius, and then this is the equation for temperature variation. Okay. Okay, let's do some example. A circumferential groove pressure fat bearing is lubricated with SAE grade 20 oil supplied at gauge pressure of 30 psi. The general diameter DJ is 1.75 inch with unilateral tolerance of negative 0.02 inch. The central circumferential bushing has diameter of dB like this and unilateral tolerance of 4 inch. The L over D ratio of half bearing that constitute the complete pressure fat bearing is 1/2, and the general angular speed is 3000 revolution per minute or 50 revolution per second, and radial steady load is 900 pound. The external sum is maintained at 120 Fahrenheit as long as necessary. Heat transfer does not exceed 800 BTU per H. BTU is British thermal unit. Okay, find the steady state average film temperature. Compare H naught, H is minimum film thickness, temperature maximum, and pressure at supply with Trumpler criteria, and estimate the volumetric side flow. Okay. Remember, there is a video on Trumpler criteria, meaning that Trumpler criteria suggests that there should be a minimum film thickness. Okay, there must be a minimum film thickness. There is the Trumpler criteria. Okay, so this is the solution. R over dj, you can get R. Just divide the diameter, you can get R. This is the clearance. This is for the equation for the clearance. Trace back the numbers. In order to understand this question, trace back the numbers you can get. Okay, and L over D equals to 0.875. P equals to this question you get pressure equal to 294 psi, and this tomography number is this equation you get 0.0579 U. Using tabulation method to find average temperature, the first trial will be this 170 F. There is one lengthy video I made on tomography number. If you can see that video, you learn from that video. Meaning that you have to calculate. There are many graphs that you have to see. In the end, there is a graph stating about film temperature. Okay. If you have the textbook with you, you can open that page on the graph on Raimondi and Boyd. Okay. Then you get this tomography number and everything. And from equation 1, tomography number equal to 0095. So you get this equation, temperature average, and then from adding second line, again you have to do trial and everything. The iteration has not closed. One could plot trial resulting T average, and then result tabulation is this. CH naught equals to this. Required for Trumpler criteria for angular speed, equation section 12.7. This equation. Okay. Okay, then you trace back all the numbers you get, and then in the end you get the side flow, you get the heat loss, and you get the torque, parasitic torque. Okay, that's all. This video, 30 minutes video on this topic. We will continue on the next topic on loads and material. Thank you very much.